Hello everyone, this is Dr. Webb and welcome to this Abstract Algebra 2 video. So a lot of the work that we're going to be doing ahead is going to be stemming from the fact that we can think about field extensions, and particularly field extensions over the rationals, as being vector spaces over the rationals, and we'll be able to use tools from linear algebra then to get new results about these field extensions. And so the purpose of this video is to review over vector spaces and some important concepts from linear algebra. And then we'll be tying some of those right now into field extensions, but we'll be doing much more of that in the coming weeks. So first, let's review the definition of vector space. But actually, this is sort of the grown-up definition of vector space. This is not the definition that you were probably given in your linear algebra class, but this is more the true algebraic idea of what a vector space is. And so a vector space is always tied to a field, so we're going to let F be a field, and then V is a vector space over F is if V is an abelian group under addition. So that means if you have two elements of V, you can add them together, you're going to get something back in V. Everything in V has a negative element that cancels it off, and you have a zero element in V. And then there's some further structure, and that's that for any element A and F and any element of the vector space V, then you can take the element of the field and multiply it to the vector. And so this actually should be a little v here. This should be a little v, not big V, a v. And then often when in linear algebra you talk about the elements of the field as being the scalars and the elements of the vector space as being the vectors. And so we're not actually going to be using those terms very much, but those ideas are still here. And so beyond that, you can do these between the elements in the field and the vectors in the vector space. You can do these operations that are like distribution and associativity in terms of the multiplication. Okay. So if you look at these, you'll notice that these are all things that are going to be true. If V was a field that contained F, then these would all be things that you could do anyways, right? So in fact, if F and L are fields and F is inside of L, then we can automatically think of L as a vector space over F, because all of these properties that are in this definition are already true about fields. So if you can think about a field as being sort of a vector space plus more structure. The additional structure is that you get to multiply just not by elements of F, but by any elements in L. And there's also more multiplicative structure. But all of the vector space facts are still there. So in a vector space, we can talk about linear combination of elements of the vector space. And so a linear combination is you take your scalars a1 through ak and f, and you take your vectors v1 through vk and v, and then if you do a1 times v1 plus a2 times v2 up to ak plus vk, that's a linear combination. This is a term that we've used quite a bit, but let's just codify it in so we know exactly what we're talking about. And then the most important idea that comes in with vector spaces with linear combinations is linear dependence and linear independence. So let's review linearly dependent sets. So a set S of V is said to be linearly dependent over F if there exists a linear combination v1 through vk and s such that we can get a1 times v1 plus up to ak times vk equaling 0, where not all of the ai's are 0. So this is some non-trivial linear combination that equals 0. So we'd call this a non-trivial linear combination equals 0. And then, so one way to think about linear dependence is a polynomial over f. If alpha is a root of it, that actually gives a linear dependence on those powers of alpha, right? So if f of x is a0 plus a1 x up to an x to the n, well, that means if you plug in alpha, this is a0 plus a1 alpha plus an alpha to the n. And then if alpha is a root, this is equal to 0. So this is a linear combination of the powers of alpha that gives you 0. So this is a linear dependence. And so really that's what being the root of a polynomial in a vector space sense means, is that if you look at the powers of alpha up to n, you have a non-trivial linear dependence between those. So if a set is not linearly dependent, then we say that it's linearly independent. So what this means is that if you take any v1 through vk in the set, the only way to get a linear combination using v1 through vk to equal 0 is if all of the scalars, all of the coefficients you used, were 0 to begin with, right? And so there's only the trivial solution. Okay, and then once we can talk about linear independence, this now allows us to talk about the dimension of a vector space. And so the dimension of V over F is defined to be the maximal cardinality of a linearly independent set of V. So it could be that you could have infinitely many things added together, or there's no finite number of elements added together that's ever going to equal 0. And so in that case, you can say that the dimension of the vector space is infinite. We're mostly going to be concerned with finite dimensional vector spaces. And so that means that there is some largest size that a linearly independent set can be for where if you try to add in one more element, then all of a sudden it's too big and you get a linearly dependent set. So now that we have dimension and linearly independence, now we can define bases. So what is a basis for a vector space? Well, a basis for a vector space is a linearly independent set, and it's what's called a spanning set. And so a spanning set just means that every element of the vector space can be written as a linear combination of elements of B. Okay, so a basis is linearly independent, and then every element of V can be written as a linear combination of elements of B. This is more often or quite often said, we'd say B is a spanning set of V. Where the spanning set, the span of a set is how many all the elements of V that can be written as a linear combination from that set. And then the important result, which we're not going to prove, this is just a result from linear algebra that you would have seen in linear algebra, is that the number of elements in a basis equals the dimension of the vector space. And so in particular, if a vector space is finite, has finite dimension, that means that every basis has the same number of elements. And so let's even put that in. If V has dimension n over F, then so n here is finite, then every basis for V will have precisely n elements. And any set that has more than n elements can't possibly be a basis, and in fact, it has to be linearly independent. And so this is one of the key ideas that actually we're going to be using quite a bit, that if you know what the dimension of the vector space is, and you have more elements than the dimension, that means that there has to be some sort of linear dependence between them. There is some non-trivial linear combination that's going to equal 0. And so one of the big theorems that's going to stem right out from this is, for our purposes, when we're thinking about these field extensions, what are bases for these as vector spaces going to look like? And so particular, if we have alpha is algebraic over the rationals, it should be Blackboard Q, with minimal polynomial f of x, and let the degree of f of x be n, then if you do 1 alpha alpha squared up to alpha to the n minus 1, this has to be a basis for Q adjoint alpha over Q. And so remember the two parts of proving that this is a basis, and this is going to be a homework problem, is showing that it is 1, linearly independent, and 2, that it's a spanning set. And so the spanning set we actually have pretty much already covered. You saw it in the last video. If you remember, last video we were actually able to prove that Q adjoint alpha looks like this, where the CIs are rational numbers. And so this right here, saying that everything in here can be written like this is showing that alpha to the n minus 1 is a spanning set. And so what's left to prove here is that this set is linearly independent. Okay. And so an immediate corollary to this, if you look and count through how many elements we have in this basis that we proved before, well, there are exactly n of them. And so the size of the basis is the dimension of the space. And so this tells us that the dimension of Q adjoint alpha over Q is equal to the degree of the minimal polynomial of alpha. Okay, so knowing what the minimal polynomial is tells us what the dimension of the space is. So instead of always saying dimension of the vector space, when we're talking about this in terms of fields, we're going to toss in this term called index. And so let L and F be fields, with F being a subset of L. So L is and you can think about L as being an extension of F. Then the index of L over F, denoted this bracket L colon F, is going to be defined to be the dimension of L over F as a vector space. And so we've actually, in Algebra 1, we saw this same term of index, particularly talking about groups. When we mod out by a normal subgroup, the index is the number of cosets. Well, so you can think about the number of cosets as sort of representing kind of the number of copies of that normal subgroup that make up the whole group. You can think about this is sort of happening in the same sense, that the index here is talking about the dimension of L over F. And so you can think about dimension as being the number of copies of F inside of L. And then once we know that what an index is, then we can define what's called a finite extension. And so an extension L over F is called finite if the index is less than infinity. Okay, so in particular, we know that if alpha is algebraic, then the index of Q adjoint alpha over Q, this is equal to the degree of the minimal polynomial. And so since the polynomial, this has finite degree, so it can't be infinite. And so Q adjoint alpha, any algebraic extension, any simple algebraic extension is going to be finite. So if you're just adding in one algebraic element onto Q, this is giving you an example of a finite extension. One of the things that is also a homework problem this week is actually proving that the other direction is true as well, that any finite extension has to be algebraic. And so, in fact, if it's finite, it has to be algebraic. There are examples of algebraic extensions that are not finite, where you keep on adding more and more algebraic terms. But if you have any extension that is finite, then it turns out that it's going to have to be algebraic. And then the last concept I want to talk about in this video is going back over the idea of linear transformations on vector spaces. So let's let V and W be vector spaces over F. Then we'd say that a map T from V to W is a linear transformation if for all vectors U and V and scalar A, we have that U plus V plugged into the transformation is equal to T of U plus T of V. And if we have A times V plugged into the transformation, we can pull that A out, and it's going to be A times T of V. So we are particularly going to be interested in linear transformations of a field onto itself, to itself. Really, these are kind of, in a vector space sense, you'd call these isomorphisms. And so let's think about this in that term. So if we have V as a finite dimensional vector space over F, and we have some basis, V1 through Vn for V, then we can think about a linear transformation, or we can represent the linear transformation as an n by n matrix. And so this is a real important part in linear algebra. And this is one of the main reasons why in linear algebra you do so much work on matrices. And so the idea is the matrix, which I'm going to call M sub T, it has these entries. And so all of these Aij's are all inside the field. So these are all Aij are all in the field. And so how do you know what A sub ij is? Well, if you look at the jth column, so if you look at all of these here, you take the jth column going down, well, the elements of the jth column come from where the linear combination sends the jth element of the basis. Okay, and so this representation depends on what the basis is. If you change the basis, you totally change what the matrix looks like. So what you do to get the entries of this matrix, to get the jth column, is you send the jth basis element through the linear transformation, and then it has to land somewhere in the vector space, so you can rewrite it back in terms of that basis. And then the coefficient for V1 is going to be the top of that column, and then the coefficient of A2 is going to be underneath it, all the way down to the coefficient of Vn is going to be the bottom element of that column. And then what's nice about having this matrix representation is now it allows us to compute what happens, how things get sent through the linear transformation. So if you have some element, you have it represented by some linear combination of the basis. And so this is This is what being a basis means. It means that every element in the vector space can be written as some linear combination of them. Well, how do you find out where that goes? Where does it end up after it gets sent through the linear transformation? Well, you can calculate that doing matrix multiplication on, so you have your matrix, and then you have a column vector, which is the coefficients coming from the representation of your element in terms of the basis. And then the column vector that spits out is going to be the representation of, I guess the arrow should go there, is going to be the representation of the element in terms of the basis again. And what's nice about this matrix is if you have the matrix and you figure out what the determinant of the matrix is, one of the things that the determinant tells you is whether or not the linear transformation is invertible. And so in particular, if the determinant is not equal to 0, then the linear transformation is invertible. And that is an if and only if statement. And so there are lots of things that we're going to be looking at which we can think of as linear transformations. And so sometimes this information that we can get out of the matrix representation will help us understand the transformations more. And so things that will turn out being linear transformations will include just multiplication of elements in the field. We can actually think about multiplication as being a linear transformation. We are also going to be studying automorphisms on the field to itself. And so any automorphism, because it is a field automorphism, it has to play well with addition, and so that means that it's a linear transformation. And so we will be using some tools from linear algebra when we study those. That is all for this video. I will see you again soon.